results from the PhD thesis Yamani did for the summer in 2 French labs, namely I2M in Bordeaux and Bamba in Angers. So, in order to increase the energy efficiency, the summer is introducing new electrical steels generations with a decreased thickness below 0.5 millimeters, a larger silicon content, and a larger grain size. And these modifications are reducing the iron losses, but they are also impacting the mechanical properties, including static strength. Moreover, due to the production weights, all electrical sheets are punched. And as you know, punched is introducing some defects on the edges. So here is a typical morphology you get on the edges, with a rollover, a shear zone, a fracture zone, and a burr. Regarding fatigue, we will be interested by these 3 effects, namely, well, the geometrical defects, as you can see here, but also hardening and residual stresses. So, in this presentation, we will try to uncouple the effect of these 3 parameters on the fatigue strength and to quantify them for our French edges. So, I will start with the material testing conditions, then present our fatigue results, and I'll spend more time on analyzing the punch sheet edge, so in order to quantify, as I said, hardening, residual stresses, and geometrical defects. Then I will say a word on how we try to model these effects on the fatigue strength. So, the material is a non-oriented iron silicon electrical steel. There are rod sheets with a thickness of 350 microns. So they have a slight rolling texture. They are about 3% silicon in it. So we get this kind of equiaxed microstructure with pretty large ferrite grains. And so we get a very ductile steel here. So if we look at quasi-static properties, we can say our material is more or less isotropic. And so we perform fatigue tests under uniaxial tension. I didn't mention that the ultimate goal is to design electrical machines for stop and start. So we are designing for tension conditions. So we used a 0.1 load ratio, but as you can imagine, it's difficult to use negative load ratio with such thin sheets. So here is the specimen geometry. In order to study the influence of the defects on the edges, we used parallel edges. So we have 2 20 millimeters long edges with homogeneous stress distribution. Most important, we used 4 different configurations in order to uncouple the different effects. First configuration are punched specimen. So we use the very same conditions as industrial punching in order to assess the resistance of our material. But we also polished some specimens in order to remove both the geometrical defects on the edges and the hardened zone. So, and this polishing, as you can imagine, also introduces compressive residual stresses, as we will measure it later. The third and fourth configurations are the same as the first and second, but with stress relief heat treatment. So, in the third configuration, we remove hardening and we relax residual stresses, so we only keep the geometrical defects. And finally, if you get a punched, then polished, then annealed specimen, you remove all of the 3 effects and you get what we will use as a reference and what we expect is our intrinsic material. So let's move to the results. Here are the SN curves, and here are the median fatigue strengths at 5 million cycles. So as you, well here, with the purple triangle, we have our reference material. Blue diamonds are for polished specimens, so we get a higher fatigue strength due to the compressive residual stresses. The worst fatigue strength is for punched specimens, of course, and so there are the red points here. And if you look at the green stars, you have the punched, then annealed specimens, so you only have the effect of geometrical defects. So here we quantify the effect of the compressive residual stresses, of the geometrical defects, and on the three effects altogether. I will just say a word about quark propagation. To say it short, it's very fast. So it takes about 2,000 cycles for 0.15 quark to propagate up to the final failure. So all the results I presented earlier are given for quark initiation. So that's why we looked closer at quark initiation sites. All quarks initiated on the edges, and for punched specimens, whatever the heat treatment, they always initiate on a punching defect located in the fracture zone. I will come back on this point later. For polished specimen, quark initiation is intergranular. So now I will explain you how we quantified these three effects, namely hardening, residual stresses, and geometrical defects. So first we made micro-hardness measurements. So as you can see here, we find hardening in about 200 microns layer close to the edge, just in the case of punched specimens. If you polish or anneal your specimens, you don't get any hardening anymore. But as you can see, the resolution is pretty low here, so you don't really have the slope and the exact evolution of the micro-hardness here very close to the edge. So we use X-ray diffraction analysis. Just a word, as I mentioned, we have pretty large grain size, so we need to use a quite large spot size for our measurements. But since our sheets are very thin, we need to use a stack of 10 specimens, and so the results I am giving are a wedge on the spot size with looking at 8 or 9 specimens. So we measure residual stresses on the top surface and then under the surface by removing some layers. And here is what we get for punched edges. So we have pretty high tensile residual stresses in the loading direction, which is also the rolling direction. And these residual stresses are the same order as the initial yield stress. And they decrease up to about 200 microns depth. And if you look at the full width at half maximum, you also see that it also gives you intel about the hardening, and you can see as it decreases also up to 200 microns. So this is the affected zone for our material. But we assume it depends also on the thickness of the material. If you look now at polished specimen, we measure, of course, compressive residual stresses, but the affected zone is only about 50 microns here. And of course, we check that annealing really relaxes the residual stresses. So here is our quantification of residual stresses and hardening. We also looked at the geometrical defects. If we look at the edge, you see that there are pretty large defects. So you find vertical scratches, but also depressions in the top surface, defects in the shear zone, but the biggest defects are located in the fracture zone. And all cracks initiate on these big defects in the fracture zone, which are about the size of 2 grains. So we assume that during the punching process, we get some grain decohesion leading to this geometrical defect. So, in order to identify the very defect on which crack initiates, we use a strategy similar to the one Frank described earlier this morning on Forge Bar Road. So we get a scan of the punched edges before fatigue testing, and then after testing, by comparing micrographs and the scan, we manage to find the exact defect on which crack initiated. So once we get the geometry, we may measure square root of the area or make some finite element calculations to assess some high cycle fatigue criteria. So here is an example with the scan before fatigue testing, micrographs of the cracked specimen, and here is the defect on which crack initiated. And of course, it's, as I said, it's always in the fracture zone. So we get the 3D geometry of our defect with this resolution. First, we measure the square root of the area in order to assess Murakami criterion. And well, I won't speak much about it because it didn't work. Mostly, we guess it's because we have very large gradients regarding hardening and residual stresses. So simply it's not suitable for this type of problem. So I will say a word about how we model geometrical defects. So we made some finite element calculations on elementary values around the critical defects. We use, well, of course we don't know the cyclic behavior of the 200 micron deep hardened layer. So we use two different hypotheses. So either the hardening is very large, so we may assume the material remains elastic, or there is no hardening, then we use the macroscopic cyclic behavior of the material. And we did our calculations and assessed a cross-land criterion. Using a local approach, we get some very conservative results. So we had to use a volumetric approach in order to average values on the volume around each integrating point. And we are able to predict the danger coefficient for critical defects. So we are able to estimate with about 8% error if we will get fatigue initiation on the crack or not. And due to the averaging, well, we didn't find any significant difference between elastic and elastoplastic hypotheses in our calculation. So let's move to the conclusions and prospects. The strength, the fatigue strength decreases about 20% due to the punching process. The contribution of geometrical defect is about 8%. The main contribution is also due to the very high tensile residual stresses, which are the same order as the yield stress. And we have a very small affected zone, and we are able to localize the critical geometrical defects in order to apply non-local criteria, cross-land criteria. Up to now, we didn't take into account the residual stresses in our finite element analysis, and well, that's another subject. That's not that easy to do. And since our grain size is about 100 microns and our sheets are 350 thick, we have between 2 and 3 grains along the thickness. So we assume that in order to get really representative results, we cannot do homogeneous simulation. So we will have to use 3% plasticity. Thank you.